In this chapter, we're going to look at carboxylic acids and nitriles. We saw carboxylic acids last semester briefly, and we've seen nitriles because we have used cyanide as a nucleophile. Let's look and see what we do know. We've already covered the nomenclature of acids and possibly a little bit of how to name a nitrile, but I'm going to go over nitriles with you as if you've never named them before. To name the acids, we count the number of carbons in the chain, including the carbon that's in the carboxylic acid functional group, and we use our prefix and end with anoic acid. So if we have 6 carbons, 5 that are in the carbon chain and the 6th is in the carboxylic acid functional group, we call it hexanoic acid. If we have a cyclohexane ring and there's a carboxylic acid group stuck on the outside, well then we call that cyclohexane carboxylic acid. And we know that when there is a carboxylic acid functional group stuck on benzene, we call it benzoic acid. With the nitriles, we do the same thing as with the carboxylic acids, is we count all the carbons, including the carbon that's in the nitrile group. So if there are 5 carbons in the alkane chain and the 6th in the nitrile group, we call it hexane nitrile. If we ever have a cyano as the cyanide as a substituent, we call it cyano. So if, let's say, on the number 3 carbon of hexanoic acid we have a nitrile, then we call it 3-cyano hexanoic acid. We also have looked at the acidity of carboxylic acids. We saw that they were more acidic than phenols and alcohols, and we saw that when you have electron withdrawing groups on them, the acidity is increased, and electron donating groups will decrease the acidity of carboxylic acids. And then we saw a few reactions that have been scattered in the other chapters as products of reactions of other functional groups. When we look at the carboxylic acid, realize that we have 2 different ways to identify the carbons outside of the carboxylic acid. There's the Greek letter denotation, which is alpha, beta, gamma, delta. And so if I look at this carboxylic acid, the alpha carbon is adjacent to the carbon in the carboxylic acid. However, if we're looking at the numbers, we count the carbon in the carboxylic acid as number 1. It's very annoying, and I think they did this just to confuse students, but that's the way it is. I'm sorry. So to form acids, we've seen a number of old ways that where we've made carboxylic acids from other functional groups. We've oxidized alkenes, we've oxidized alkyl benzenes, we've oxidized primary alcohols and aldehydes. We have seen the hydrolysis of nitriles, but it's been kind of briefly introduced in the previous chapter, and we'll go into this a little bit more in depth. And in this chapter, we're going to see that we can carboxylate a Grignard reagent. So let's take a look at that. Here are some of the old reactions. On this first one, we see an alkene, and the alkene is treated with an oxidatively cleaving set of conditions. Potassium permanganate and water does this. And what happens? We cleave anything that has a hydrogen on the carbon in the double bond, that carbon is turned into a carboxylic acid. If we have a primary alcohol, we can treat that with chromic acid, and that turns to a carboxylic acid. Aldehydes can be treated with either chromic acid or potassium permanganate. And what do we get? We get it oxidized all the way down to a carboxylic acid. And anytime you have an alkyl chain in which there is at least 1 hydrogen on the carbon adjacent to the benzene ring, and you treat it with potassium permanganate and water, what do we get? We get the whole chain is oxidized down, boom, to a carboxylic acid group. It doesn't matter how many carbons are there. Just so long as it's not a tertiary carbon. If it's tertiary carbon, there will be no hydrogen, so there's no reaction. We've seen already that nitriles can be hydrolyzed in the previous chapter. But let's look and see how we can make nitriles. In the previous chapter, we added hydrogen cyanide across a carbonyl and made a cyanohydrin. But this you might remember from our old way back last semester. We can do an SN2 on a primary or secondary halide, and we get a nitrile. What's really neat is that nitriles can be easily hydrolyzed to a carboxylic acid with acid, and we can also hydrolyze with base, and it will give us carboxylic acid. Note that what we do effectively is we take an alkyl halide and we add a carbon to the chain. Although it is derivatized to an acid, we still have lengthened the chain by 1. Remember that when we do nitrile SN2, you have to have an unhindered carbon. So primary works best, secondary is okay, but primary does work best. If you have a tertiary carbon, the sodium cyanide is going to be basic enough that you're going to have some elimination occurring. So you wouldn't want to use tertiary at all. Okay, let's look at acid or base hydrolysis of nitriles. You can see that we can use either base to hydrolyze a nitrile, or we can use acid to hydrolyze a nitrile. You pick whichever set of conditions would give the least interference with other functional groups on the compound. This is a really neat thing that Grignard reagents can do. If you ever have a Grignard reagent and you bubble carbon dioxide through it, the carbon dioxide actually inserts between the carbon and the magnesium. See, this carbon dioxide gets inserted here between the carbon chain and the magnesium. After you form the carbon dioxide adduct, once you wash with acid, it protonates it and you get a carboxylic acid. And like the nitriles, you've just extended your chain by 1 carbon. So here's an example. We have a secondary halide here that we're treating with sodium cyanide. We're getting an SN2. Here they have basic hydrolysis of this, washing with acid to get rid of the base afterwards. And notice this nitrile gets changed to this functional group. And do you see how you added a carbon to the chain? Here is a carboxylation of a Grignard reagent. Here's phenylmagnesium bromide. We're treating it with carbon dioxide. And what do we get? We get insertion of the carbon dioxide between the carbon and the magnesium. And when you wash with acid, we have added a carboxylic acid or a carbon and as a carboxylic acid. So you can add a carboxyl group through either a halide going to a nitrile and then to a carboxylic acid by hydrolyzing the nitrile, or you can add it by taking the halide to a Grignard reagent and then using carbon dioxide to make it into a carboxylic acid. When do you use them? Well, you can use either as long as there's no conflict with the functional groups that are already in the molecule. The nitrile, because it's SN2, works really well for primary halides. And if you had something that would be protic that would react with a Grignard, you'd want to go the nitrile method. The Grignard reagent is going to be really good for secondary and tertiary halides because a tertiary halide isn't going to undergo an SN2. Secondary is kind of slow with the SN2, and you might have some reactions you wouldn't want having happen. So the Grignard reagent works really well for that. But you have to make sure there's no protic groups that would react with the Grignard. So this is something we just did in the last chapter. Keep it in mind. You can take a carbonyl and change it into a cyanohydrin with hydrogen cyanide and then hydrolyze it and see what you did. You added a carbon. It is a carboxylic acid functional group, and it's kind of easy to recognize when you have done this from a carbonyl because it's going to be an alpha hydroxy carboxylic acid. So let's try a Okay, how can you prepare cyclohexane carboxylic acid from cyclohexene? Well, the first thing you want to do is write down the cyclohexene and then write the cyclohexane carboxylic acid. How do you think those can be related? Well, one of the things you might think of is that this could have come from a Grignard reagent. That would require that you had a bromine, which you then treat with a Grignard reagent, and then with carbon dioxide. There's another way. You could have used the nitrile intermediate. And if you use the nitrile intermediate, that's fine. Okay, so now how do I go from one intermediate to another? Well, for the first step, I just use hydrobromic acid. Once I have hydrobromic acid, I can treat that with magnesium and then carbon dioxide and wash with acid, and that gives me cyclohexane carboxylic acid. Well, how can you prepare 3-hydroxy-2-phenyl propanoic acid from styrene? Again, let's write down the styrene and then write down the 3-hydroxy-3-phenyl propanoic acid. Well, when I look at this, I think, well, maybe this could have been a nitrile. If that was a nitrile, what could this have come from? Well, this could have been a bromide because I know I can add bromine and water across this double bond, and it would give me Markov-Natakov addition for the water across the double bond. So what conditions do I need to go from styrene to this hydroxybromide? Well, just bromine and water would do it. And how do I go from this bromide to this nitrile? You can do an SN2, that's primary. And then to go from this nitrile to the carboxylic acid, I could use either acid or basic hydrolysis. Is there another way to do this synthesis? Probably. And most likely you might have thought of something else, and that's fine. Don't feel like you might have something that you can't have done. I just now thought, well, I could have formed the epoxide and then opened the epoxide with sodium cyanide. That's another possibility. So there's all sorts of things you could have done. So how can you prepare this acid from 3-bromocyclohexene? Well, let's first put the 3-bromocyclohexene down, and let's draw this acid so it looks more like it's in a ring. Now I can kind of see where the functional groups come from. So I can see that this is where the bromine used to be, and this is where the alkene used to be. And suddenly I think, well, this alkene could do oxidative cleavage, and this bromide, well, that could be from nitrile displacement. SN2s on the end of an allyl group are very fast. So let's go ahead and look at what intermediate we might have. We might have this intermediate, that's the oxidative cleavage, and then maybe this intermediate, because I can do SN2 on an allyl carbon very quickly. What conditions would I have? Well, sodium cyanide would give me this SN2. Hydrolysis would give me the carboxylic acid. And then potassium permanganate and water would give me this final product.